Hi everyone, thank you for joining me. The following is a video tutorial for how to complete the Screw Simple Machines lab with Onshape. First step, as always, is to log into the Glenbrook South Enterprise on Onshape. Next, navigate to your team folder. I'm just going to go to POE Gold 3. Find the Screw Simple Machines lab project folder, and in there you should find the start file for this lab. Right-click on there, copy the workspace, remove the word copy at the end. At the very beginning of the document name, put your first and last name with a space and a dash. As that populates here on this tab, I'm going to switch over to my second tab just to give you a quick preview of what the completed version of this lab is going to look like. So here's a quick look at the finished assembly. You can see how all the parts are connected together. And essentially what we're going to do is animate the slider constraint. So if I go to animate this, I can animate it at about 3 inches, at steps maybe 50. Hit play here just to give you an idea of what this is going to do. So as the screw rotates, it's going to go back and forth. Actually went a little too far there with 3 inches in that one direction. But basically you get the idea here. We're going to send this rack and pinion setup back and forth by rotating the worm gear and have that translate from rotary motion down into linear motion back and forth. The resistance is applied straight down onto the rack piece as it's moving back and forth, and our effort would be applied to the worm wheel here. So I just kind of attached it out front to show the general idea of where those forces would be taking place. So if I stop the animation and move back over here to my second tab, everything is loaded up. There is a drawing sheet which we will end the tutorial with. On that drawing sheet, there are 3 questions relating to this particular setup. What is the circumference of the worm gear? I provided the diameter here on this drawing sheet using a detailed view from this view up above. What is the pitch of the worm gear? Also provided you with that dimension with a detailed view from this view. And then lastly, what is the IMA of this screw assembly? To complete this assembly, starting from the very beginning, the first thing we're going to do is attach these standoffs to the metal plate, and that's going to create the support system for the worm wheel. The first constraint that we want to apply is going to be to these standoffs, and I'm going to do that by using a fastened mate. I'm just going to grab the center point here on the top of the standoff, and then there are 25 holes from left to right. It's going to be a little imbalanced either way you cut it. So what I'm going to do is put this 11 spaces in and then 1 row towards the center. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 1 in towards the center. This is my particular point that I'm going to use right in the center. And then just hit the flip button so that the standoff is on top. Check mark. The next standoff that's going in, I'll do the same thing. Grab that top center point. We're going to need to create a gap of 2 spaces. So I'm just going to count 1, 2 in the middle, and then it's actually going to go on this third one down. Get that attached, flip it so it's standing up on top. So again, we've just created a separation of 2 rows here between standoffs. For my next 2, again, grab that top center point, and we want to skip 1 row down the center this way. So I'm going to go right there with my next one and flip it so it's on top. Check mark, and 1 more standoff to go. Grab that top center point. Same gap from the other one. Right here is where I want it to be. And flip that up. So the reason we're putting them in these exact locations is because of the bearing block, which will go in next. That's going to connect from left to right across this assembly. And then in the other direction, we need enough room for the worm gear and the axle to all kind of fit and be nicely centered. So next step is for these bearing blocks to go ahead and get mounted to the top of those standoffs. I'm going to grab the center point for one of my holes. And then back here on the standoff, I'll just grab one of the top points here on the standoff. And that actually came in perfectly. I got lucky with that selection. So that's exactly where I want it to be. I'll go and get my next one. Do the same thing, grab that point. It actually looks like it grabbed the middle point there. So I'm gonna deselect that mate point and then make sure I grab the very bottom of that hole. That'll be a little easier. And then back over here on the top of the standoff, select that point for mounting. It came in perfectly oriented, so I'll just hit the check mark for that. And we haven't done this yet, but I thought, why not? Let's go ahead and include some of the screws. So in real life, if we were putting all these things together, you of course would want to use some screws. And an appropriate size screw for this would be our 0.375 inch screw. So you see that over here on the left in our parts list. I'm going to go ahead and get those fastened into place. The trick for this one is if you just rotate to the bottom half of the screw, you can actually grab that point right there underneath the cap of the screw at the top of the cylinder. And so that's what I would want to select for that, and then put it down inside the hole there based on that top point, make the selection, and the screw goes in exactly how you would expect it to. So you just repeat that process 3 more times. So 1, check mark to finish the placement. I got 2 more to go. Make that point right there, selection. Put it inside the hole, check mark, and 1 more screw to go. Rotate so you can see the bottom, grab the top of the cylinder, and then put it inside the last hole here. Oops, make sure we grab the right point. There we go. Okay, check mark. Those are all in place. Very good. Now we can go ahead and bring in the axle. So I'm going to do a rotary mate, a revolute mate. Grab the end point of that axle shaft. And then over here, remember that with these bearing blocks, if you grab this outside point, it's actually on an angle. So you want to make sure that you can get the center point of the hole itself, have that inserted, and then we will need a little bit of an offset here so that it's not kind of hanging off to the right side more than it should. So an offset value of 0.25 should do the trick. Nicely balanced on each end then. So 0.25 in the Z direction for that offset. Check mark, it's in position. At this point, we can go ahead and bring the worm gear in. That'll be my next piece. I actually had to borrow these parts from outside of this part library that I had here, so I had to go and find them by going to insert and saying other documents, and basically searched on the public domain for the VEX rack and the VEX worm parts and the components there, and I was able to find them. So added them to our tutorial. By doing so, I actually don't have the ability to edit these parts in any way. I tried downloading them from Onshape and then reinserting them, but it makes them into STL files, and there's really not a whole lot you can do with that either. So unfortunately, because we're not the owner of these parts, there's nothing that you can really change about them, like the color or anything like that. But in any case, to get this attached, I'm going to do a fastened mate. I'm going to grab the center end point here of that square opening, the hole for the shaft. Make sure you grab the center on that, and then down here on the axle shaft, grab the center end point there. We will also need to do a little offsetting. So for this one, in the Z direction, we should be looking at 0.625. Like I might need to go negative. And then just kind of rotate and make sure that looks like it's kind of nicely balanced into the center there. So negative 0.625. Check mark, that's in position. Okay, almost complete here. We have a couple more tasks to cross off the list. First, I want to get this rack put into this slider here. So they call this the VL slide. There are other components that we would normally use in conjunction with this metal piece. They didn't have them here in the digital software either. So this is going to be a fine application. Basically, we're going to line up one of the holes here underneath our rack. So let's go ahead and do that. Grab a fastened mate, center on one of those holes on the bottom, and then I'm going to mount that to the third hole here on the slide, right on the center. All right, sitting on top just the way I want it to. Check mark to finish the placement. And from here, we're going to do a linear pattern and just repeat that rack piece 4 more times or 3 more times. Let's go ahead and do that. Linear pattern. The instance is just going to be this one rack piece. The direction, you can select anything that's basically moving left to right here on the screen. For the distance, we're going to set that to 2.493. I had kind of eyeballed that number out from before, and it ended up creating a nice gap or a minimal gap between the parts. So that's the number I suggest that you use. And I said 3 a second ago. We're actually going to make 4 copies of this. So we will have 5 of them on the slide all together. So check mark to finish that. At this point, we're going to have to use a slider constraint to get this slide and rack assembly put right underneath and position it kind of floating in air. If you saw on the finished example here, there is nothing really supporting that slide piece, and that's where I mentioned typically there's other components that we would use kind of in conjunction with this so that you can mount it properly. But for this purpose and for the lab purpose, really just want to focus on using a screw and doing some rotary to linear motion with you. So I'm not going to obsess about the fact that there's nothing technically supporting the slide rail here, and so neither should you. But we are going to use a slider constraint for the slide. Funny is how that works. Let's go ahead and get that set up. Slider mate is next. What I'm going to do is select the endpoint bottom. So like right in the middle on the end of the slide on the bottom half of this. This is the point that I'm going to select. And then over here at the end of my base plate, going to do the same type of selection on the end, but on the top. And so that will get us nice and centered right underneath that worm wheel. The only thing we're going to have to worry about is offsetting the height a little bit so that those parts kind of meet and look like they're meshing together perfectly. So for the offsetting value in the Y direction, we're going to play around with this number here just for a moment and see exactly where these pieces come in. I'm going to hit the green check mark just so I can update the preview and see how much overlap I have between the worm wheel and the rack piece. There's just a little bit there, more than I would be comfortable with. So I'm going to go back to the slider constraint. We're going to create a little bit more separation, which means we need to lower this value. I'm going to slide a 2 into the middle, call that 0.225. You can see that updated a slight bit. Let's see. Yes, if I update that, really close, I think for safe. Just to play it safe, let's go ahead and drop that one more time, and I'll slide a 1 inside of there. So 2, 1, 2, 5. Check mark. That creates a nice gap. Okay. So now we have those in position. The last pieces to our puzzle are going to be our resistance and effort forces. I'm going to apply those using a fastened mate. Grab the tip of the red arrow. And if you zoom in close enough onto just one of these teeth, you can actually grab the centroid for that surface. So I'm going to go right on the center. And I think I didn't grab the arrow from before. Let's go ahead and do that one more time. There we go. Check mark to place it. Do the same thing on the opposite end. Grab that tip of the arrow. Center point here on the rack on the very end. Okay, and then last but not least, we're going to apply our effort force. And if I zoom in close enough to the bearing block, there's a nice flat surface right here that has a centroid symbol right on center. So I'm going to grab that, and then we'll just do a little bit of an offset so that those parts aren't glitching through each other. So in the Z direction, maybe a 1/4 inch offset just to back it off. I'll do a -1/4 since it moved further in the direction that I didn't want it to. And still glitching out a little bit. Let's go ahead and do 0.5. All right. Check mark, looks good. There's the finished assembly. We have our slider constraint in position. We have our rotary constraint in position. The last thing is to set up this rack and pinion relation for our example. So I'll go ahead and pull that up on the screen next, rack and pinion. To make this work, we will have to select the revolute and the slider. And my number for this one is going to be 0.315 inches. Hit the check mark. And then we're going to drive this based off the slider constraint. So I'm going to pull up animate here. We're going to check our animation and see how well we did. As far as the value that it's going to go back and forth, we could probably get away with 3 now. It didn't work out a little earlier when I was doing my demo with my completed version because of the spacing. But as I created this video for you folks, I kind of made sure I was a little bit more centered. So for the animate constraint, we can do 3 inches as our end value. For steps, maybe bring it down to 50, and then we can let this reciprocate so it goes back and forth. So there we have it, going from 0 to 3. We could actually change this to -3 to 3. That would be interesting. Let's go ahead and see what that looks like. So traversing a much longer distance there, you can see that screw is actively rotating very fast so that it can make its way up and down the track with that rack and pinion setup. So this is a finished version of the assembly, and then the last thing for you guys to do is to move on over to this drawing sheet and answer those 3 questions I mentioned towards the beginning. So based on the diameter, what is the circumference of the worm gear? What is the pitch of the worm gear? That is the dimension right there that I gave you. And then what is the IMA of the screw assembly? Remember, that is circumference over pitch. Thanks for watching. Hopefully you enjoyed this tutorial, and I'll catch you guys next time.